The F-18 fighter jet has something called LEXs. These stand for leading edge extensions and are also known as LERXs, which stand for leading edge route extensions. What do these do? Why does the F-18 fighter jet need them? And what happens when they don't perform as hoped? That, my friends, is what we're discussing today. And this is the first podcast of the year, so Happy New Year to all of you. So let's move on. I also hope that 2024 is a more aerodynamic year for you than 2023. Anyway, so to look into these LEXs and what they do, we're looking at a technical report actually, from the Air Force called Effect of Leading Edge Extension LEX Fences on the Vortex Structure over the F-18. This was written by a chap called D.H. Thompson, who when starting this had little more than a pocket full of coins and a heart full of dreams. And now look what he turned this into. Actually, I don't know if it's a he or she, but if it is a she, then it wouldn't really work with my this was written by a chap introduction that I had. So let's move on. Anyway, this report was done on a 1/9 scale of the F-18 at moderate to high angle attack, and that last part moderate to high angle attack gives us a clue as to what these LEXs do. And along with this 1/9 scale in the wind tunnel, this researcher also tested a 1/48 scale in a water channel. Now I should mention that this is a very long document, it's 64 pages. So what I'm covering in this podcast is just to do with the LEX aerodynamics, but there's quite a lot of good stuff in there on other things, like just general wind tunnel stuff and that kind of thing, and also flow viz techniques, which I really suggest that you read because you will learn a lot from flow viz techniques. They're really cool, and you can find this paper in the link in the description. So what are LEXs exactly, and what do they do in general? So LEXs are these flat plates that extend from fairly upstream along the fuselage, so about here, like near the cockpit on this particular aircraft, and then they sweep all the way along to the start of the wing and join the wing in a nice smooth fashion. They can vary in size, ranging from very small to almost like 10% of the wing. So you can see here, these LEXs, for example, extend all the way from the start of the cockpit to like where the engine would be, even further downstream, like around the engine perhaps, like the midsection. So these LEXs are usually very highly swept, and the leading edges are very sharp. They work very similarly to delta wings, and if you don't know what delta wings are, they are wings that are shaped like the Greek letter delta, a triangle, hence the name delta wing. So we've done a podcast on delta wings before called, all the way back actually in our 8th podcast, which is called Delta Wings Can Do What Other Wings Can't. So check that one out if you're interested in what delta wings do. But just in a nutshell, what delta wings do is that they create these strong vortices that travel over the suction side of the wing. These vortices are created because of the highly swept leading edges, and because these leading edges are very sharp, just like LEXs are. Typically, one vortex on each side of the centerline forms, and these vortices are very low pressure, as in the case with the centers of all vortices. They have these low pressure cores, and that sucks the air down onto the surface because you have this wing which has these vortices over the top. That's even more low pressure, and the flow going over the top, which might often separate, will actually get sucked down more. So it's a bit more of a like a pull down for it to help you produce lift at high angles of attack. And for some delta wings, like they can go to like 50 degrees or 60-degree angle attack and still have some decent amount of lift. That's how effective these vortices are in producing lift and letting the plane fly at high angle attack. It's crazy. And that is kind of like what LEXs do too. They create these vortices that travel along the top side of the LEX and each side of the fuselage, then make their way down over the rear of the wing around here, and ideally they suck the flow down to the wing here, so the plane can fly high as attack and not lose lift. So that makes the plane much more maneuverable as well. Also, apparently the vertical fins, so if you have like an airplane with these vertical fins at the back, the upright parts, they interact with these vortices to some extent, and these vortices can affect the fins in a positive way and a negative way. What this researcher here says that the LEXs, these vortices coming from the LEXs, can interact with these vertical fins and actually result in the fins producing more side force, so they're laterally more stable at higher yaw angles. In other words, these vortices are not only aiding lift, but also maneuverability in this way. And that's clever engineering, folks. But not everything is all peaches and cream for LEXs. In fact, under certain conditions, like what can happen over delta wings, the vortices might burst, and that leads to a loss in lift as well as unsteady flow that can impact other parts of the plane. I should also mention here that if you like this podcast, hit the subscribe button or follow button. And also, we just released the OpenFOAM course of ours, which teaches you how to use OpenFOAM. You find that link in the description, so check that out. So anyway, back to this report. this researcher, who I don't know the name of actually, starts with D, his first name, so I'm guessing it's going to be Dougal. So Dougal in this report says that this breakdown can affect the tail fin and make it shake, so that's a negative effect. And this results in this tail becoming weaker over time, so it affects its fatigue life. This fatigue life is just how long something can withstand being cyclically loaded. So to overcome this problem, the developers of the F-18 added something called LEX fences. So this fence is literally a flat plate that stands upright along the LEX and parallel to the leading edge. So it will just go along like this, like the guys in the cockpit or the girls in the cockpit looking out the side. You see the LEX, and then on there there's this flat plate sticking up, going longitudinally as well. So for some reason, this dramatically reduced the dynamic loading on the downstream path of the plane when the vortices burst. However, it is unknown why they were so effective. In fact, these fences were designed through trial and error. But even though little theoretical forethought went into these LEX fences, relatively speaking, these fences didn't affect the maximum lift and only increased the drag a little bit. So I don't actually know much, because Dougal just says a little, like it affects these maximum lift and drag a little bit, but that's still pretty good. And these fences had little effect on the static longitudinal characteristics. So the static longitudinal characteristic means just how much the plane wants to nose down or nose up. So that's just a fancy way of saying that. So one downside of this fence is that it increases the radar deflection when side on, which makes the plane more visible to radar. Now, he said that he used FlowViz to study these LEXs with fences, and he added many pictures from his work in this report, but the pictures are so hard to make out. I mean, you'd have an easier time figuring out why that artificial raspberry taste never tastes really like raspberries than decoding some of these pictures. And you can't really see too much in a lot of them. But fortunately, there are other data reported too, and we can feast our eyes on that. And another thing that is interesting in this report is that this research was done by the Australian military, but I found this report on the US military website, so I don't know what is going on there. Anyway, one of the major reasons why understanding why this LEX fence works so well is because it is obviously important to understand how to make airplanes more stable, including fighter jets, because if this jet is in a dogfight or something, and all of a sudden has a dramatic change in force reduction, that is going to be hard for the pilot to control and even predict. And also, actually, on page 8, when I was reading this, I could see actually Dougal's real name. It's David. So there you go. Some mysteries solve themselves. Anyway, let's move on to the experimental setups and discuss them. So David says that his 1/48th scale model of the F-18 was actually a plastic hobby kit that was modified to make it more representative of the real thing. So you know those little plastic kits that you get, they can like piece together? It was one of those things. And we don't have an actual picture of it, but this is approximately what it looks like. And I love when researchers do things like this, because it's like thinking out of the box to achieve a goal still. The only thing that would have made this better if he made it out of duct tape. So to make this thing more realistic, one thing he did was that he put plastic tubes in the model, and then he had them terminating at various points along the surface to actually get these surface tappings. He then pumped dye into these tubes so the dye would be injected into these regions, and then you can see where the flow went from there. He said that he had an internal duct also that led from the start of the engine inlet to the corresponding exhaust nozzle. So in real life, we obviously know that the turbofan engines that these fighter jets have obviously take in air through the inlet, then they combust some stuff and throw the air and the mixture out the back. In many models, you don't get that connection between the inlets and nozzles like those plastic models that kids buy. So obviously that greatly affects the accuracy of the model. But here, this guy actually did that. He went back and he decided to put this tubing in to then connect these two. But while you might think that huzzahs are in order at the moment, just wait, because he went even further. He then connected the engine to suction pumps to simulate the right amount of fluid going through the engine. That is awesome and really detailed and accurate work, Dave. Well done. And of course, along with the original plastic hobby plane, he also added the LEXs with these LEX fences with brass. So in addition to adding dye to visualize the flow, Dave also used hydrogen bubbles, which is where you place this long thin wire in the water, and through electrolysis, you get really tiny hydrogen bubbles, which then travel downstream, and then you can see the flow. And this, to be perfectly honest, is such a rare thing to see. I actually have never seen met anyone who has done this before, except me. I actually did this a long time ago, and one reason why you don't see this too much is because I think a lot of people think that it's an outdated technique. probably because of how simple it is. Like you literally have just this wire, usually a tungsten wire. You put two electrodes on like one side to complete the circuit, stick it in water, and then that creates the bubbles. But if you do it well, it is very effective at showing you where the flow is going and what is happening. So like Dave here, I've also used it to investigate vortices, and it's very effective for that. One of the main problems though that arises from hydrogen bubble flow viz is that you don't want to get the bubbles too large, because the larger they are, the less they follow the flow. And in fluid mechanics, this is called following the flow faithfully. So it's a funny term, and I don't know why this exact term is used given the connotations, but maybe the person who came up with it was being cheated on or something, I don't know. So she thought that it was an appropriate term. Anyway, that's the word faithfully. And you use this for not only hydrogen bubbles, but PIV and LDA, like all these seeding particles that you put into flows. If they follow the flow well, they're following the flow faithfully. So anyway, Dave here gives a really good technique for determining where to place the dye injection ports. So the main problem is, where do you put these ports? So you remember how I just said that he drilled holes into the surface, put these tubings in there, and then pumped dye through there to see where they came through. Well, how do you know where to put these things? Because usually you want to put them where the most important flow features are, but how do you know where they are if you haven't tested the model yet? So there's chicken and egg kind of problem going on. So Dave gives a good idea how to overcome this, and that is to put oil dots on the surface of the model and run the test briefly. From here, you can see where the fluid is moving to, and then that tells you where you would like to put these ports. So maybe a couple of hours work helps you understand how to make your entire experiments better. That's a good trade-off, and very smart. So from here, Dave could ensure that the dye injection ports were put in the right places and injected into the vortex cores. And I must say that this research was very well thought out from this aspect. So one thing that I'm a little unsure about is the Reynolds number of this model. So in the water channel, you really can't run the water at very fast speeds. So Dave put this model in wind tunnels and water channels. So here, in fact, Dave had it at 80 millimeters per second. That gave a Reynolds number based on the MAC, the mean aerodynamic chord, of only 5,120. That is a few orders of magnitude off from real life. So would that affect the vortices breakdowns? Most likely. I mean, generally vortices break down due to viscosity, and the Reynolds number is a strong indication of how dominant the viscosity effects are. And actually, if you don't know what the Reynolds number is, check out a video on our YouTube channel called Aero Fundamentals Number 2, Reynolds Number Explained. In that, we go through exactly what the Reynolds number is and how it works with surface roughness and thermal density. So having a Reynolds number like 100 times lower than what it should be would definitely affect how a vortex breaks down. In terms of this particular case, I'm quite certain that the vortex breaks down due to the flow field and not because it hits something. So I do think that the vortex breakdown seen here will not be exactly the same as seen in real life. But Dave also tests a 1/9 model of the F-18 in a wind tunnel, and runs it at a Reynolds number 130,000 based on the mean aerodynamic chord. So that would be about 260,000 maybe based on the entire length of the airplane, maybe a bit more. So the fact that he is testing this across different Reynolds numbers is a good sign, because then you can see whether the general trends are holding between these two different Reynolds numbers, and then you can sort of apply it to full scale if so. Now the final question about doing this is what regimes the Reynolds numbers are in. So for example, if you do a test at Reynolds numbers of 5,120 and then one at 10,000, that isn't going to make that great a difference to the results, and it's going to make the results that much more trustworthy, because yes, while you have these Reynolds numbers are different, they are still very much in the laminar regime. And yes, you do have the vortices, which will make the flow more turbulent, but most of the flow around the airplane, including upstream, is still going to be laminar. On the other hand, if you were to test at a Reynolds number of 5,000 and then one at 130,000, you now have two different regimes, laminar and transitional flows. That means that if you get the same phenomenon across this large range, then that is a good indication that the results are very robust and will hold at the full scale Reynolds number as well. So for the wind tunnel, the model was configured to replicate flight at an angle of attack of 25.6 degrees and a Mach number less than 0.6. To do that, the leading edge flaps were deflected at 34 degrees, and the trailing edge flaps were not deflected at all. So that's quite interesting. At above 25.6 degrees angle attack, the trailing edge flaps aren't deflected. That's pretty interesting. So Dave also used a couple different flow vis techniques. The first one is the smoke flow vis, which I think is everyone's crowd favorite. The second was oil film flow vis, which is where you have this viscous liquid, often a kerosene and flaxseed oil mix, with some form of dye or powder in it. And then you put it onto the model surface and run the wind tunnel. You can then see where the flow is, because of where the oil is going. That is being transported by the fluid, and that's effectively where the fluid is going. And then you can see the surface pattern. So this technique gives you so much information, and in fact, yours truly has also used this technique in his PhD thesis to great effect, and it's my personal favorite, partly because it's so informative, and partly because it's so easy to do. So, like, literally, if you go into a wind tunnel and you do this for 2 days, like just this oil film flow vis, you'll have more flow vis data than you know what to do with. Like, you'll be sifting through it for like a year. There's so much information in it, and it's very useful. So I highly recommend people doing this as well. FlowViz is kind of on the way out with PIV and CFD these days, but FlowViz is still very important. You can get a lot of information out of it, and very quickly and cheaply. So the acceleration and pressure of the vertical tail fins were recorded, and there's a little bit more information missing from the setup though, such as the blockage ratios of the models in the water channel and wind tunnel, at least from what I can see, and also what is the free stream terms densities of these flows. I don't really know what they are. I'm not sure if that's a big problem for them, because this report was mainly for an internal report and not a public report. So maybe they knew about all this stuff in their own little circle, but the public doesn't know. Anyway, it would have been nice to see for our information in hindsight. So another major limitation of this study, as Dave points out, is that no attempt was made to make the model's fins have the exact same structural characteristics as the real F-18. So when it comes to the vibration frequencies, that changes the results a lot, but I guess the main reason why he didn't attempt to get the same structural characteristics in the fins was because this work was more about the general effects of the fences than the exact effects. So let's move on to the results. Let's go to figure 5 and 6, so these ones here. So in figures 5 and 6, we see the effects of the fence on the fin accelerations. The power spectral density is given, which is also referred to as PSD, and power spectral density is really just how much power a certain frequency has. So in terms of sound, which uses the exact same thing, the higher the PSD is at a certain frequency, the louder it will be at there. So like if you have 50 hertz and it's a PSD of like 50 decibels or whatever, that's obviously more than 40 decibels. So here the greater PSD is at a certain frequency, and the more energy then the fin will be vibrating with. So you can see here this sort of peak here. Now, these figures give the effects of the LEX fences on the fin tip acceleration with different speeds ranging from 30 meters per second all the way to 50 meters per second, and two different angles of attack, 25.4 degrees and 30.5 degrees. These ones, for example, are for 25.4 degrees and 30 meters per second, and then we can go all the way down and find the other ones down here as well. So one thing we see for all configurations without LEX fences is that a peak occurs at one particular frequency. So we can see here, a peak here, a peak here, and continually on. That means that we're probably getting some kind of resonance in the wing, so maybe we're matching that frequency there perhaps. But when you put on the LEX fence, the power of this vibration always reduces. So the amount that it reduces depends on the flight conditions, but there is always a good reduction. So for example, when the plane's at 30 meters per second and an angle of attack of 25.4 degrees without the fence, which is this one here, so without the fence, the PSD has a peak frequency of almost 9 Gs squared per hertz. But when you put the LEX fence on, so now this figure here, that drops to by about 65% to about only 3 Gs squared per hertz. So comparing that when the plane is now at 40 meters per second and an angle of 30.5 degrees, so let's scroll down to that one now, which is this one here. So compared to here, so when we have no fences on, the PSD without these LEX fences is about 225 Gs squared per hertz, but with the LEX fences, it drops to about 30 Gs squared per hertz. So a whopping 85% reduction with these LEX fences. That's how much the vertical fin is now reducing in terms of its vibration. It's like 7 times vibrating less power in the vibration than if you had no fence. That is how good these LEX fences are reducing fin vibrations. Now, along with the change in the magnitude, there was also a consistent change in the vibration frequency a little bit. So this change wasn't consistent because sometimes it was increased by a few hertz, other times it was reduced by a few hertz. So for example, here in figure 6b, we can see that without the LEX fences, the frequency that it was vibrating at was maybe about like 70 hertz maybe. Then when we put on the fence, it was maybe about the same maybe there. But if we go down, we can now see that it's a little bit different. So this was maybe about a bit under 70 hertz. This is a bit over 70 hertz. So there's a few hertz difference here that it changed in the vibration frequency. Now, I'm not sure why this occurred. Is it something to do with the structure or the finished structure, or with the vortex breakdown, or just error in the equipment? I don't know, but it's interesting that vibration peak frequencies change a little bit with these fences. Now let's move on to figure 7, because we see the location of the vortex breakdowns at different angles of attack. So right here, with fences on, fences off, water tunnel, and wind tunnel. First thing is that the results from the water channel, and I say, but water tunnel here, is very much the same as from the wind tunnel as well. So that's a good indication that there is quite a lot of robust nature to the flow physics across Reynolds numbers. But one major trend that we see is that as the angle of attack increases, the position at which the vortex breaks down moves upstream. So at a 10-degree angle of attack, the vortex breaks down right on the tail's vertical fin, so right here. When you crank the angle of attack all the way up to 45 degrees, the vortex now breaks down almost immediately, like literally just a few feet from the start of the LEX, like right here. It doesn't even get close to making it past the LEX, the very thing creating it. And this relationship is very linear, so we know that when the breakdown position is at two extreme angles, 10 degrees and 45 degrees, but if you were to take it in the middle, like 27 degrees or something, then that corresponds equally in terms of linearly where the vortex breaks down. So that's pretty cool. Now, Dave also wanted to see if the addition of the fence changed the vortex breakdown, and surprisingly, it didn't. So I mean, you're literally sticking this plate in and around the vortex, and it doesn't really affect the breakdown point. In terms of fences on and off, they're the same whether you have the fence on or off. The black dots, black diamonds, and the clear dots and diamonds lay on the same kind of line. So that is quite surprising that the fence didn't really affect where the vortex was breaking down. Now, having said that, if we look at figure 8, we can see these figures here. Let me zoom out a bit so we can see both of them. There we go. We can see here that the water channel results from the flow vis where the vortex breaks down along the F-18 with and without fences at an angle of attack of 19.5 degrees. So these pictures aren't that clear, but I think we can make out what there is to see. So while we saw that the fence didn't really affect the point at which the vortex broke down, I would say that it does affect the vortex breakdown process. So if we look at figure 8a here, we see that the vortex breakdown is very sudden. It goes quite like this line here. Let me zoom in for this one. It's quite steady, this line. This is the die, and then all of a sudden it just breaks down. On the other hand, if we go to figure 8b, let's scroll down to this bad boy, we see a bit more of a gradual breakdown. So it's fairly consistent, and it breaks down a little bit instead of just like flaring out so suddenly. So sure, these vortices start to break down at the same point regardless of where the fence is, but to me it seems like it takes longer for the breakdown process to occur when the fences are on, so this bottom figure, compared to when they're off on the top figure. So looking at figure 9, I think a similar conclusion can be drawn. So these figures here, again, like these break down very quickly compared to these ones are quite gradual. So what do you think? As a side note, Dave also agrees with this, I think. I mean, he pointed out that they differ and said that the fences cause a helical deformation of the vortex core. But we should stress that Dave says that this is when the vortex breakdown occurs downstream of, this only occurs when the vortex breaks downstream of the fence, not upstream. He says that if the vortices break down upstream of the fences, no changes are seen in the vortex breakdown nature between if you have fences on or off. Now, that is where we come to really low quality figures like figures 9, D, and F. So let's scroll down to these ones, which kind of are supposed to show these things, but the figures are really poor quality, so I can't really see squat. To be perfectly honest, like here, I can't see too much here. It's a lot of white, maybe a little bit of change, I don't know. So to be perfectly honest, I can't really see what's going on, so I don't know how to tell if that's the case. I guess Dave would know better because he was witnessing it live as well as seeing pictures, whereas we only have dodgy pictures to look at. So some of these pictures, the quality of them are like the poor quality UFO sighting pictures, where the UFO could be anything, including nothing. But let's conclude that the fences do affect the vortex breakdown if the vortices break down behind the fences. Now let's move on to a really cool flow feature, how the LEX fence causes a secondary LEX vortex. So you not only get the vortex from the LEX as usual, but also a second vortex, and so you get two for the price of one. I like that. So figure 13, let's go down, I think maybe around here, even more. As I said, this document is very informative and there's a lot of information here, so it's pretty cool. So anyway, figure 13, A shows the pattern of the dye coming from the ink dots on the LEX. So this is supposed to be the LEX here, and at least that is what the authors say. I mean, I can't really tell too much about what's going on here, but they have figure 13 here, which shows a sketch of the flow pattern around the LEX with the fence, and this is really informative here, so this is really cool. The first cool feature that we see is that we get a normal LEX vortex here, in very close to the fuselage. Then around the LEX fence, we get a very small vortex forming as the flow from inboard of the wing like whips around and then around the outboard section, then over the fence and curls up into a vortex. That is a small vortex though. But we do get another much bigger vortex forming around effectively the last bit of the LEX before it joins the wing, just around here. This second big vortex then twirls around the first vortex, the first normal LEX vortex, then goes downstream. So figures 14A and B and C show these topologies and just how much the flow wraps around the fence. So you can see here, this is without the fence. The flow is quite like going in one direction. Then you have with the fence, and see how much it just whips around here. This is the surface pattern coming from the dye. This is how cool oil film flow viz and dye patterns are. You can see so much. So I guess this second vortex is a main reason why the vortex breakdown is different when it breaks down aft of the LEX fence. And that, my little analysis, is the end of this podcast. We saw some really cool flow viz, and you can pick up a lot of tips as to how to do flow viz here. Another really cool flow viz researcher, actually sort of seen, I've heard someone call him like the godfather of flow viz. I never heard anyone else call him that, so I don't know if it's true or not. But it's a guy called Henri Werle, which is a French guy, so like Henry the French way with an I on the end. Werle, W-E-R-L-E. If you want to see some really cool flow viz, check out him and you'll see some really amazing techniques along similar to this, but even better. And if you want to learn flow viz, check that out. And also, if you thought that this podcast was cool, hit the like button and click the subscribe or follow button. And big news, as I mentioned, we just released our OpenFOAM course. If you don't know what OpenFOAM is, it's the best free CFD software out there, like by a country mile. It is so good that it is just as good as the major CFD softwares like Ansys Fluent and Star CCM+, and in some cases even better. But there is one major benefit to it, and that is you don't have to pay for licensing. So the commercial softwares might cost you $50,000 per year for a license, and in fact, at some companies, like some that I've worked for, they were paying like $1 million for licensing each year. OpenFOAM, on the other hand, is completely free. You can use 1 million cells, 10 million cells, 100 million cells, 1 billion cells, whatever you like. All free. But the major problem with OpenFOAM is that it's very hard to learn. That is why we made our course, which literally takes you step by step from even installing the software all the way to doing DES simulations. So we cover geometry, importation, meshing, solver settings, and even post-processing. All this step by step that you can literally follow along step by step with us as you learn OpenFOAM. So in my opinion, learning OpenFOAM is the most important skill that you can have in CFD, because no matter what happens, you can still use it. So let's say you have $50,000 to spend on CFD licensing for the year, and instead you spend it on chewing gum or something. Well, it doesn't really matter because you can still use OpenFOAM. So you can literally sit there chewing your gum all year long while still doing CFD. Happy days. So you can find that course in the link in the description, and make sure to take it if you don't know OpenFOAM already. So that is the end of this podcast, amigos, and I'll see you next one. Peace out, amigos.